Hi. So in this video, we're going to look at topics 5.5 and 5.6. 5.5 is just talking about the collision model, which is the model that we have for how reactions work. When you talk about a reaction, how does it proceed? We know that it has to have a collision in order to proceed, but not just any collision will do. We talk about that it must be a successful collision. What makes a successful collision? Well, there's a couple different things that a collision must have to be successful. The molecules or species that collide must be in the right orientation, and they have to have sufficient energy to break the bonds or to start the reaction going. So when we talk about why don't all collisions result in a reaction, it would be because that they don't have the right orientation, or they're not at enough energy to start the reaction. We will eventually call that activation energy. So this is just a picture from the textbook, and you may have seen an example like this before, where definitely as you increase the temperature, you increase the rate of the reaction. We know that. But why and how? So first of all, we can talk about the why, because the collisions, more of those collisions are going to be successful. More of those collisions are going to have enough energy to start the reaction happening. In a rate law, how does that get translated to the rate law? Well, that would be with K. And you can see in this example how K changes, the rate constant changes as the temperature changes. And in fact, it increases. That's why in all these problems, they will always specify a temperature, but we don't really use that quantitatively. But that's because that K in the problem is only applicable at that temperature. So this graphic here just shows how orientation is important. That if you have the green atom colliding with another green atom, we can see that this is an effective collision, and afterwards you have a new product. If that similar reaction happens, but that atom of chlorine does not collide with another chlorine atom, you can see that it just bounces right off. Right? No collision, or the collision takes place, but it isn't a successful collision. So anytime that you can increase collisions, the chances are is that you're increasing the number of successful collisions. That's why stirring and surface area and concentration increase the rate of a reaction. You can't really do anything to increase the orientation factor besides adding a catalyst, which is one of the things we'll talk about right at the end. And when we talk about reactions and how temperature affects reactions, it's also important to talk about reaction energy profiles. That's topic 5.6. And all this is a graphic way in order to look at the progress of a reaction happening from reactants to products. So this is what a typical reaction profile will look like. You will see that the y-axis is potential energy, or you can just think of it as energy, and the x-axis is reaction progress, reaction pathway. It might have different names depending on the textbook or whoever created the graphic, but basically the reactants are going to be on the left-hand side and the products will be on the right-hand side. And so this is looking at the transition from reactants to products. And you can look at this reaction. You can see delta E is negative. That means that this is an exothermic reaction. But what is this right here? Well, that's the activation energy. Activation energy is the minimum energy needed for the reaction to take place, the energy that the collision must be in order for the reaction to take place. And so sometimes the analogy that is given for this is like if you're at a mini golf, if you're playing mini golf, you really sometimes have to whack that ball to get it over the hump. So this is an exothermic reaction. Overall, it releases energy, but that doesn't mean that it always happens. The reaction must be able to overcome this activation energy. Think about every combustion reaction that there is. Those are all exothermic reactions. So why is it that anything that you're looking at, the paper, wood, all those things will burn, and they will burn exothermically? So what is preventing it from spontaneously combusting right now? And that's that activation energy, right? That you need to give it a little bit of energy to sort of get it over the hump. You can see in this case, we're basically just switching around in this reaction, the nitrogen to the carbon. So the first thing that has to happen is this bond right here has to be broken. And that's what the activation energy does. It breaks the initial bond. Right here you see, what is this? What do we call that? It isn't a reactant. It isn't a product yet. So sometimes you will see it called an activated complex. You might also see it called a transition state. Those are two words that really are interchangeable with each other. It's what do you call it when it's in the middle of reacting. And then as the new bonds form, you are left with the products, and the products have less potential energy than the reactants, right? If you were doing bonds broken minus bonds formed, it would come out to be a negative number. But what that doesn't include is this idea of activation energy. And when you think about the idea of activation energy, then it makes sense why when you increase the temperature, you increase the rate of the reaction. Because more molecules will have enough energy to overcome that activation energy, right? This is that Maxwell-Boltzmann distribution that we look at all the time. And it shows us that at a higher temperature, more molecules have more energy, right? There's always some molecules that have very little energy, no matter what temperature there is. There's always some molecules that have a lot of energy, no matter what temperature it is. But with the red line here, you can see when we heat up the system, more molecules have more energy. And now we can say more molecules have more energy to overcome, that's the wording that we would use, to overcome the activation energy. That's why reactions speed up as the temperature increases. There is a way to quantify this, how relating K to activation energy and temperature. This is called the Arrhenius equation. It is not on the AP exam. They mention this in the essential knowledge just to understand that temperature increases the rate of a reaction mathematically through K by changing the value of the K. These can show us this is one of the ways that you can calculate activation energy. If you're like, how do you even calculate that? If you know the rate constant at one temperature and the rate constant at another temperature, you can calculate the activation energy. You do not need to know any of these formulas. We will never use them. So let's do a couple practice problems on this. This is sample exercise 14.10. Consider a series of reactions having these energy profiles. Rank them from slowest to fastest, assuming they have the same value for that frequency factor A. Some reactions, that's like A is taking into account that collisions and that orientation piece. So really this is just, we're looking at the only other factor, which would be activation energy. So slowest to fastest, slowest would be the highest activation energy. So activation energy is sometimes symbolized by E sub A, meaning energy of activation. So if we look at the activation energy here, we see that the middle reaction 2 has an activation energy of 25 kilojoules per mole. Reaction 1, so you're just looking at this height here, is 15. And then for the one on the right, we're always looking at the distance. The activation energy is the distance from the beginning to the tallest peak. You don't even need to look at the products. So the activation energy for reaction 3 is 20. You can see reaction 1 and reaction 2 are exothermic, while reaction 3 is endothermic. And a lot of students want to say that, well, an endothermic reaction will happen slowly. And that is not necessarily true at all. There's something else that goes on that factors into all of this besides this energy that we're thinking of, this delta H or heat energy, and that's the idea of entropy. That takes into that plus the enthalpy will determine whether a reaction takes place at all. What determines whether the reaction takes place quickly or not is that activation energy. So the slowest reaction will have the highest activation energy. That's number 2, with a activation energy of 25 kilojoules per mole. So this would be slow. This would be, number 1 would be the fast one. And then the number 3 would be in the middle. So if we were ranking them from slow to fast, it would be 1, 2, 3. The first reaction would be the fastest. The next question is a multiple choice question. Which of the following are true? They've started taking this type of question off of the AP exam, but it's still a good practice for us. So basically you just read each of those 3 statements, 1, 2, and 3. I always put like a T or F or a check somehow, and then at the end look at the answer choices. The activation energies for the forward and reverse reactions can be different. Well, that is true. So we didn't talk about that, but if we look back at this reaction, think about what is the activation energy for the reverse reaction. Well, the reverse reaction would be starting with products. And so if we were looking at what is the difference between this height here and this height here, well, it would be 15. So of course, you can have activation energies different for the reverse reaction. Assuming A is constant, if both activation energy and temperature increase, then K will increase. It would depend upon how much they increase and what there's too little information to say that it will always increase. Certainly if temperature increases, then the K will increase, but does it increase more to sort of compensate for activation energy? And then the last statement, for 2 different reactions, the one with the smaller activation energy will necessarily have a larger value for K. That's not necessarily true because K is also dependent upon temperature. So we need to look at, well, what is the temperature? And also, if it's 2 different reactions, that the constant that takes into account orientation factor and things like that, that if they're 2 different reactions, it's really hard to compare them. So I would say that the right answer here is A, that only one of those statements, the first statement, is true. So that's the end of 5.6. The next grouping are a whole bunch of learning objectives together.